Good morning, everyone, and thank you very much for joining. Compliments to two previous speakers, really good stuff there. Hopefully I can do mine justice as well. Air conditioning efficiency is the subject of my talk. This is who I am. Some of you know me already, and these are some of the things that my company and myself specialize in doing. I see so much in the way of huge energy consumption in the field when I'm working on large chillers, 8,000 kilowatts at the hospital and 12,000 kilowatts recently at a ground source heat pump installation. And I'm really concerned about the huge amount of energy that goes into efficient systems, and more concerned about the wasted energy for those that are not so efficient. So let me see if I can try and bring some of the facts to your attention that might be helpful. So I'm going to concentrate on the compressor, the refrigeration circuit, and the secondary circuits. By secondary, I mean the chill water that runs in and out of the chiller on the primary side, or the air that runs over the condenser on the condenser high pressure side. So, and what we're describing here also really applies to refrigeration systems and heat pump systems. The principles are all the same, as many of you are aware. Quite frighteningly, in 2015, the International Institute of Refrigeration calculated that over 17% of the world's global electricity is consumed by refrigeration, air conditioning, and heat pumps. And we really have to reverse the world climate change. It really is quite serious. We were talking about this 30 years ago on our refrigerant safe handling courses about rising sea levels and so on and so forth. And here we are 30 years later, and we really need to do something about it. It's also one of the Institute's key objectives, energy reduction. So that's its focus, perhaps over a period of 2 years now. So I'm going to show you a number of graphs that show varying system performance at different evaporating, condensing, and superheat values. I'm not going to cover subcooling, that would expand this talk too much. But initially, I'm using here CoolPak software, which is quite a neat product. It enables you to put in your operating parameters of a refrigeration cycle and see exactly what's going to happen to cooling capacity, heat and rejection, power input, and its COP. But really importantly, this all assumes a perfect compression cycle. So keep that in mind as we move through these slides, which I'll try and do fairly quickly. So there's an extract from CoolPak running on R410A, and here's my perfect refrigeration cycle. I want 5 degrees C evaporating, 50 degrees C condensing, only 5 K of superheat, 3 K of subcooling. And if I move on, you'll see the values there, 146 to 180. If I assume 1 kilogram of refrigerant running around this system every second, that's 146 kilowatts or 180 kilowatts of heat rejection. And I've got a nice discharge temperature of about 76 degrees C and quite a respectable COP at 4.35. So there's a summary of that particular system and my intended system design, which I'm quite happy with. I've got an efficient compressor and the capacity is based, as I say, on 1 kilogram a second running around the refrigeration circuit. I now move on to the same circuit and I've moved one parameter. My 15K superheat is really a bit too high. So what are the effects of that? Well, here they are. There's my 15K, 10K higher superheat than it should be. My cooling capacity theoretically goes up. Well, that's great. My heating and rejection is also going up. But unfortunately, my evaporator and condenser are not sized to handle that change, point number one. Point number two, when we look at the compressor performance and efficiency, we will see that that, in fact, declines. So theoretically, this looks very good, but in reality, it's not. The discharge temperature for the compressor is also now higher, up to 85 degrees C. So compressor will be less happy about that. Now I actually keep my superheat at 5K, and I've now dropped the evaporating temperature. It's too low. Instead of 5 degrees C, I'm evaporating at 0 degrees C. And what are the effects of this? So lower evaporating temperature, my cooling capacity falls, only a couple of kilowatts. Heat of rejection is up a little. My COP has gone down to 3.75. This is not good. Discharge temperature has not changed too much, but the compressor efficiency will suffer as a result of this change. Why could the evaporating temperature go down? Block filters on an air handling unit or a fan coil or a DX cassette, or lack of chill water flow, etc., and block strainers. Many reasons for that. Now I have an even worse situation. My evaporating temperature has fallen and my superheat is too high. Here are the effects: 10K superheat higher, and the cooling capacity is actually up theoretically from to 152 kilowatts. Sounds good. Heat of rejection is also up, however, and my condenser will not be able to handle that, nor will the evaporator. So the compressor will suffer even more than before. Here I've now got a nice evaporating temperature. I've got 5K superheat, that's all good. Unfortunately, my condensing temperature is now up to 60 degrees C. Maybe I've got air recirculation problems on my chiller condenser, or the condenser coil is blocked, or one of the fans has failed, etc., etc. So what are the effects now? My cooling capacity has dropped quite considerably, down to 121 kilowatts. Heat rejection is also down. The compressor will really suffer under these circumstances. Moreover, the discharge temperature has now gone up to 91 degrees C. Now things get even worse. My condensing temperature is up, and also my superheat. So now looking at the situation, cooling capacity has really dropped, now down to 130 kilowatts. COP has dropped seriously to 3 instead of 4.35. Compressor will suffer, and the discharge temperature is now 100 degrees C. Now I go to 60 degrees C condensing, and I've got a low evaporating temperature, but a respectable superheat. Cooling capacity is down to 119 kilowatts. My heat rejection is down. Compressor is really seriously suffering now. The COP is disastrous at 2.65, and my discharge temperature is at 92 degrees C. Next one, we combine all of these: low evaporating temperature, high condensing temperature, and 15K superheat. So my cooling capacity is down to 127 kilowatts. Heat of rejection has fallen. COP is only 2.68, and the discharge temperature has crept up to 102 degrees C. So how is the compressor affected by the changes in that perfect cycle? So looking at that perfect cycle and the refrigeration software there, the effects I considered were evaporating temperature, the condensing temperature, and the superheat. Of course, refrigerant charge and subcooling are also factors that will have an impact in the way that I've described, but I've not included them here. Here's a performance window, or an allowable operating limits window for a well-known manufacturer's scroll compressor. This is a large machine. It's approximately 200 kilowatts capacity. And we can see here at the line that's running in this direction, if you can see my cursor, I hope, that if I evaporate at 0 degrees C, I can actually condense as high as what looks to be about 65 degrees C. So that's the maximum allowable limit in this particular compressor. And indeed, if I plot these lines onto the chart, I can see at 5 degrees C, I can condense at 65 degrees C condensing, 0 degrees C evaporating, still the same. But if I try to drive down to -5 degrees C, then evaporating, then my condensing temperature must fall to 58. If it doesn't, the compressor is seriously out of limits and in danger of failing. Here's the cooling capacity chart, which basically sets out the parameters that drew the graph in the preceding slide. So it shows the cooling capacity running along the top there. We've got the evaporating temperature from -20 to +20, and down the left-hand side, our condensing temperature as low as 10 degrees C and up to 65 degrees C. So we can plot our parameters for our system and our intended design to see, A, are we within allowable limits, and what will the cooling capacity be at certain parameters? In this case, 0 degrees C evaporating and 60 degrees C condensing. And with this compressor, I can get 111 kilowatts of cooling. However, if I now move to -5 degrees C through system aberrations, block filters, inadequate chill water flow rate, block strainers, a failed evaporator, and so on, then if I attempt to condense at 60 degrees C, I'm actually out of limits. So there will be a cooling capacity. It's not dedicated or shown here on the chart, but it will suffer, the compressor will suffer adversely as a result. Here you can see the cooling capacity at 0 degrees C evaporating, and the effects of 50 degrees C condensing, 134 kilowatts. So now by raising the evaporating temperature by only 5 degrees, we get a tremendously improved performance. This means with a high cooling capacity, the machine will run at a much better efficiency, and it will also run for shorter periods of time. point that Ian made in his presentation. So the energy consumption will drop dramatically, as well as CO2 emissions. Here is the power input chart, and this is really interesting. So again, it shows the evaporating temperature range across the top. It shows the condensing temperature range down the left-hand side. And then if we plot at 60 degrees C condensing the power input, you can see that the power input changes very, very little as the evaporating temperature goes up. So the impact on evaporating temperature is not that great. In fact, I'll go back to that slide. However, if you look at this from a condensing point of view, if we stay with 0 degrees C evaporating at 61.5 kilowatts power input, look how the power input drops dramatically as you reduce the condensing temperature, almost in 5 kilowatt steps. So keeping that condensing temperature down is critically important from a power input point of view. We've written our own calculator for looking at condensing temperature effects on screw compressors and other compressors. And here you can see the difference. We have a cooling capacity here of 337 kilowatts if we have a condensing temperature of 50 degrees C versus 282 kilowatts with a condensing temperature of 60 degrees C, which really illustrates the point. Now moving on to the actual heat pump using the compressors that I've actually shown you. This is a ground source heat pump of around 250 kilowatts alleged capacity. Along the bottom line here, you can see the evaporating temperature bouncing around about -3 degrees C. The faint blue line is the chill water coming in from the ground source at about 7 degrees C, and the leaving water after its refrigeration effect of just under or around 5 degrees C. Here is the superheat at 10K, thereabouts. So the first thing that is obvious here is that there's a really big difference between the entering chill water temperature at 7 degrees C and -3 degrees C for the evaporating temperature. A typical normal chiller, not a heat pump, might have water coming in at 12, going out at 6, and the evaporating temperature might be 0 degrees C. You have 6K temperature difference between the leaving water temperature and the evaporating temperature. Here, this difference is much larger. And we've then proven that, in fact, the chill water flow rate is too low. The disappointing thing about this installation is that it's fitted with an electronic expansion valve as well. These were invented and conceived in order to reduce superheat from 5 to 7K, that normally achieved by mechanical thermostatic expansion valves, to bring superheat right down to as little as 1K. And here this device is set at 10K, which is an unnecessary waste of energy and good cooling performance and compressor efficiency. Now we move on to the same heat pump. It's a twin circuit machine. And we have here at the bottom, the power input, which is at around just under, say, 60 kilowatts, 55 kilowatts or so on average. In fact, there are two power lines there. They're actually one superimposed on the other. Both compressors receiving the same chilled water source are behaving in the same power input method. Above, we have in the dotted line the COPs, the blue and the red line here, and also then you can see the cooling capacity of each circuit. Note how the two are following each other exactly the same. So whilst they're at different capacity levels, cooling capacity in the upper one is reaching almost 200 kilowatts and the lower one at 150 for different reasons. They're both following in the same pattern because there are aberrations occurring in the chill water flow rate and temperature. So this is primarily part of the cause of the problem that this machine has suffered. And as a result of its suffering, this is the damage that the scroll compressors have experienced. So fractured scroll compressors, out of 12 compressors, 10 have actually failed at this installation. So a guide to maximum system efficiency and reliability, just closing out now. Here are some quick tips. I won't read them all out, but if you have DX systems without a liquid receiver, for example, these are the things that we could do to thoroughly improve the performance of our systems. All obvious to many refrigeration engineers out there in the field, but hopefully the graphs that you've just seen and the previous elements of the presentation will amplify the need to execute all of these steps when designing systems, servicing them and commissioning them in the field. Or if it's water chillers and chill water systems, these are some of the things that we really should concentrate on in order to maximize the efficiency and reduce our CO2 emissions. Again, I won't read them out, and this presentation will be available for you to look at these at a later stage. We also need skills, as was mentioned earlier. So for 31 years, we've been training and certifying engineers, really dedicated to helping people understand all these things and gain all these skills. So these are some of the skills and knowledge factors that are needed in order to execute proper and efficient servicing, maintenance and troubleshooting of air conditioning and refrigeration systems. Then also our engineers in the field need good tools for commissioning. So good manifolds with temperature sensors measuring superheat and subcooling, flow meters for water and air on chillers and DX systems, maybe some form of portable performance analyzer that has the capabilities such as we see here on the right. This can look at a system efficiency in total, show you the refrigeration cycle efficiency, how efficient the compressor is working, what the condenser is doing, and what the evaporator is doing. This is called System Efficiency Index. It's a far more sophisticated method for measuring system efficiency as opposed to COP. The thing is, if we cannot see how precisely well a system is running, how can we possibly hope to make it run efficiently and reliably? So we must tool up our engineers with all the essential instruments that they need for doing their job properly. So that's it from me. Hope you enjoyed it, and thank you very much for your time.